Hi folks, welcome back to Calculus 2. And before we get started, I want to apologize for the huge delay in my video making. I know it's been a really long time since I made my last video. Can't even talk right now. That's how excited I am. And it's just mainly because life has not been easy for me over the past month or so. It seems like everything bad that could happen to me has happened. And I'm not going to go into detail. I'm going to post about it probably on my blog, and maybe in about 8 months from now, that's a conservative estimate, check back on my blog for a year when I finally have information there about it. And I was able to drown my sorrows in about a half gallon of peanut butter ice cream from Blue Bunny. Not a sponsor, by the way, but it is delicious. It's helped me out of a few different binds in my life. So enough about my extremely fascinating life. Let's get into the math. So in this video, I'm going to be talking about how to integrate a variety of rational functions. And what do I mean by rational functions exactly? Well, let's make sure my computer wants to behave itself tonight. I sure hope so. Sometimes I have to threaten to throw my computer out the window if it does not want to behave. So by rational functions, I mean something that has this general form. Something over something else. And most commonly, this form manifests itself as some kind of a polynomial over some other kind of polynomial. So for example, you could be dealing with something like this. I'm meant to make that a 3, and then I change my mind halfway through, and then I change my mind back again. That's how my mind works sometimes. We could have something like this. No, I want to make this maybe something different. Maybe you make that a third power, and then we have 2x squared minus x plus 1. Keep it simple. So this is one of infinitely many examples of a rational function. We could have something like this, or we could even have something a little bit different. We could have a higher power on top than we have on the bottom. So suppose we have something maybe like this. And in this case, we would have to do some kind of a division. We would have to either do a polynomial on division, or we would have to do a synthetic division in order to break this down into a much more manageable form. We would have to employ some modularity to break it down into small manageable pieces whenever the degree of the polynomial on top is higher than the degree of the polynomial on the bottom. And then we can also have trig rational functions, believe it or not. We can also have maybe something like this. I'm going to keep it simple for now because it's late and I don't trust my judgment at the moment, so I'm going to keep it very simple. We could have something like this. And you might be thinking, well, there's not much we can do with it. At first glance, yeah, it kind of looks like it. But what if we were to employ some of those super useful trig identities that we all love so much? All those trig identities our pre-calc teachers made us memorize because they're going to be super useful one day. Yeah, right. So what if we were to turn tangent of x into sine of x divided by a cosine of x? But before I go fancy with that approach, I'm going to rewrite it like this first. Let's say this is tangent of x. And speaking of tangent, I know this is a particularly long tangent, but for the main topic, so I'm not going to go too far into it, I promise. So let's say we have something like this. Tangent times 1 over sine of x. It's a tangent about a tangent. Yep, I am trying to be funny. So let's say we write tangent a little bit differently. Let's say we write tangent as sine over cosine. We're going to use one of those quotient identities that is not remotely close to an n. Forgive me. So we're going to use one of those quotient identities. We're going to write tangent as sine over cosine. And then you might be thinking, hey, well, then that means we can simplify things quite a bit, which is really nice. We have a sine of x on top. Upstairs, we have a sine of x downstairs as well. The upstairs cancels with the downstairs. We're left with 1 over cosine, which is just the secant function, secant of x. And there are a lot of things we can do with this, but this is a calculus video, so we're going to be mainly focusing on the integral applications of these particular types of rational functions we're going to be talking about today. So let's say we were given something like this. Let's say you're being asked to find the integral of 5x plus 1 divided by 2x minus 4 dx. So up to this point, we don't really have any practical tools to directly tackle this thing head on. If we had a degree on top that's higher than the degree on the bottom. So see how we have a degree 1 linear polynomial downstairs, and then upstairs, what if we had this be a quadratic? So we know we could use some of our nifty pre-calc tricks in this one. We could do some long division or some synthetic division. By the way, I'm going to be posting links to my previous videos covering synthetic division and polynomial long division. They're going to be in the description in case you want to brush up on either of those topics. They are pre-calc topics, yeah, but they're going to be quite helpful in this video and the problems we're going to be seeing over the next few class periods. So I lost my train of thought. So let's go back to what we had before. So we had this before. Something with just a single degree on top. This is an x to the first, and then another single degree on the bottom. So it doesn't really seem like there's a lot we can do with this one. I mean, we might just want to flee in terror and just pull up Wolfram Alpha. Wolfram Alpha has always got our backs, right? Well, there is a way to do this yourself. There is a way to be tricky, be strategic, and integrate this completely on your own without a computer. So you might see something that might be helpful right away. One of my most brilliant students saw something like this, and he says, well, why don't we just break it up into two separate integrals? And then I had that look of deep, deep pride. I always get when one of my students says something like that. One of my students picks up on something really awesome that a lot of my other students don't see right away. It just swells me with pride with one of my students comes up with something like that. So he's absolutely right. We can break this up into two separate integrals because we have a binomial on top. We have two distinct terms, which means we can break it up into two separate integrals. So we're going to have 5x over our common denominator, which happens to be 2x minus 4. You get a differential. And then we're going to have plus. This is just going to be 1. So instead of just having 1 upstairs in the denominator, I'm going to actually move our dx upstairs. It's not completely necessary, but my OCD mandates that I do it like that. And then we have that same common denominator. So from here, it may not even be super clear what to do next, especially with the first of the two integrals we just created. So we can simplify things quite a bit. So we have a 5 on top. We have 5 times x. We can move that 5 right out front and makes things just a little bit nicer to deal with, a little less scary. And then what we can also do in the denominator is notice how both of our terms are factors of 2. Both of our coefficients are factors of 2. So let's go ahead and factor out a 2 from both of those. So instead of a 2x minus 4, let's go ahead and change that into a 2 times the sum, or I should say the difference, x minus 2. It's equivalent to 2x minus 4. So let's go ahead and work some magic and simplify it in this way. And you might be wondering, why is that useful? And the reason why it's useful is because we can think of this as 1/2 times everything else that involves variables, everything else that involves x. So this is 5 times 1/2 times this variable expression on the inside of the integral. We can actually do something that makes things a little easier for ourselves. We can move the 1/2 out front. So that way, instead of having a 1/2 inside the integral, we're going to have a 5/2 on the outside. So it's going to look just like this. So we have 5/2 times this integral. And we're still not quite in the position that we want to be in yet. We can't quite do anything with it just yet without any substitution. We're going to have to do a u substitution for this first one. So remember that it's always in our nature to set u to be whatever happens to be in the bottom. Whenever we have a rational function like this and it's a u substitution situation, we always want to set u to be whatever happens to be on the bottom. We can't have a u be on top because we can't have a du be on the bottom. Du always has to be on the top for u substitution to function correctly. No pun intended. Maybe it was intended. So I want to set u to be everything that happens to occur on the bottom of this first integral, our very first, everything that happens downstairs. So we're going to have du. No, I'm getting ahead of myself there. It's the sugar rush from all that ice cream. I gained God knows how much weight. I'm just fat and happy. That's all I care about right now. So u is going to be everything that happens downstairs. X minus 2. And then if we were to take the derivative of all that, we get just 1. So I'm going to be clever. I'm going to move the dx to the other side by subtracting both sides by dx. But then we still have that thing on top that's a little tough to deal with. We have the dx being taken care of. That's just du. But what the heck are we going to do with the x right there? So remember, in an integral, We can have things only in terms of one variable. We can have everything in x, or we can have everything be in u, or we can even be fancy or have everything be in theta, or everything in terms of t, or in terms of w even, or v. But we can't have an integral in terms of two different variables, at least not in anything I'm going to be teaching in this particular video. We have to have everything in an integral be in only one variable. We're not going to be doing any Laplace transforms or any kind of Fourier series. So we're going to be sticking with one variable, which means that if u is our variable, we're going to have to do something with this x. We're going to have to put x in terms of u somehow so that we only have one variable that we're dealing with. So if u is equal to x plus 2, I'm going to be clever. I'm going to add 2 to both sides, and we're going to end up with this. U plus 2 equals x plus 0. U plus 2 equals x. So now what we can do is we can rewrite this very first integral. We're going to have 5/2 times the indefinite integral of x. I'm going to change x to u plus 2. And then on the bottom, we have x minus 2, which is just u, and then du is dx. So life is good. Life is fantastic. And then we can do something similar with the second integral. So I'm going to take out the factor of 1/2 because we can see we have a coefficient of 2. We have a coefficient of 4. We can take out a 1/2 in the same exact way we took the 1/2 out of as a factor from the denominator of the very first integral. So I'm going to rewrite the second integral. I'm going to make it plus 1/2 times integral of dx over, instead of 2x minus 4, we take the 1/2 out of everything. So it's going to turn it into just x minus 2. Fantastic. So let's take this bit by bit. Go back to the first integral. We can simplify things quite a bit. We're going to do something similar to what we did in the first one. So remember, we're still doing the first problem. I meant the first step of the current problem, the first step of this problem. So remember, we broke it up into 2 separate integrals. We did the denominator, or the first part of the numerator, over the common denominator. And then we added the second part of our numerator over the same common denominator. We broke it up into 2 separate integrals. So we want to do something similar with this one. So we can do, well, u over u is pretty simple. That's just going to be 1. Doesn't matter what u is. U over u will always be 1. So I'm going to break it up into 2 separate integrals. So I'm going to have 5/2 times first integral. Well, u over u is just going to be 1. So I'm going to make this into a 1 times du. And then the second integral we have, that's going to be 2 divided by u. But don't forget, we also have that 5/2 being applied to not only the first integral, but everything that happens on the inside of the integral. It should all be multiplied by the 5/2. Which means that if we're going to apply some modularity and break it up into multiple integrals, we have to make sure that we are multiplying everything by that constant. Otherwise, we won't get the answer we're looking for. And this part works out pretty nicely because notice how we have a 1/2 being multiplied. We have basically 5/2, that's 5 times 1/2. And then we have a 2 right there. The 2 on top is going to cancel with the 2 in the 5/2, meaning we're going to get just 5 times the integral of 1 over u. So this 2 is going to go away. And this 2 on the bottom is also going to go away. And I'm going to be fancy. I'm going to move the du to the numerator now. And it has no effect on the outcome. We have not changed the value. We just made it look a little bit nicer. So now let's go ahead and do the math. So we're going to get, oh, I forgot to write the other integral, plus 1/2 integral. And then we need to do some kind of a substitution here. We've already done u substitution. So I'm going to do what I call a w substitution. You know, some people choose v. I just prefer w because v gets used a lot in integration by parts. I like to stick to only using v typically when I'm doing integration by parts. So that's why when I'm doing a substitution problem like this, I prefer w to v. So I'm going to set w to be everything on the bottom. Typically it would be u, but u is already being used. So I'm going to use w as my variable for this next part. So w is going to be equal to our nested function in the bottom. It's going to be x minus 2. And then the derivative of w with respect to x is going to be just 1. So then dw is going to be dx if we multiply both sides of the differential equation by dx. So now let's go ahead and substitute everything in. So dx is just dw. dw. And then everything on the bottom is going to be w. Sorry, that was a stupid joke. I don't know if you guys remember Arthur. but I am really, really old. I'm not proud to say it, but I'm ancient. I'm probably going to be making all of these references that you guys are just like, what? What's this guy talking about? So never mind. So let's continue. So this first integral, if the integral of dx is just x, then the integral of du is going to be u. It's going to be 5/2 times u. That's what we get when we integrate du, we get u. In the same way as how we integrate dx, we get x. And then we're going to have plus 5 times the next antiderivative. So the antiderivative of 1 over u is going to be natural log of u. And you don't have to put it in absolute value bars. I just try to be overly cautious because we know that the natural log function can't accept any negative values. So I just put the lines there to show that we're only giving it positive values for the argument of the function. The argument only accepts positive values. And then we're going to have plus 1/2, the same thing, where this is going to just be natural log of w. And then we need that constant of integration, because this is not a particular solution. This is a general solution. We can call this a family of solutions. We don't know if there was a constant there before, and if there was, we don't know what value it is. So that's why we put c there, because whenever we take the derivative of a constant, we get 0, and that's why we don't know whether or not there was something there before, without this being an initial value problem. So let's substitute everything back in. So we have 5/2 times u, and u is just x minus 2. Plus 5 times natural log of u. And again, u is just x minus 2. Plus the next part, it's going to be 1/2 natural log of w, which conveniently enough also happens to be x minus 2. Plus c. And this is a calculus class. I'm not going to take off points from my students if they left it in this form, but if your OCD is kind of off the charts like mine, you can actually combine this term together with this term. So 5 is the same as 10/2. You have 10/2 times this natural log function plus 1/2 times the very same natural log function. So if you were to add those together, you would actually get 11/2 times the natural log of x minus 2. So you would be able to condense them quite nicely into just one expression, one term involving the same natural log function, involving natural log of x minus 2. All right, so like I said, I'm not going to take points if you don't go that far. I'm mainly just concerned with my students understanding the calculus part of this, understanding the integration strategies. So this would be perfectly fine. You would get full points on my exam if you left it like this. All right, well, that was fun. Let's see if we can have some more fun. Let's see. What if we had something like this? Minus 25x dx. So one of the main goals of this video is to look at many different kinds of rational functions and have enough practice and enough applicable skills so that we can look at something and tell right away what strategy might be useful. So it's always a really super good idea to try u substitution because it is really versatile. It helps us solve problems really, really quickly if we're able to do u sub. It's always a really good idea to check if you can, because if you can, great, you'll save yourself a lot of time and a lot of headache. If not, that's how you know for sure you're going to have to do some other kinds of methods of either simplifying this before integrating or doing some kind of advanced integration strategy if u sub doesn't work. So in this case, it looks like u sub might work. So let's set u to be everything we have in the denominator. And then we'll see if it works nicely. So then the derivative of u with respect to x is going to have to be, this is going to be x squared minus 25. Fantastic. And then I'm going to multiply both sides of the differential equation by dx, which gets us this result. So now let's go ahead and substitute everything back in. Life is good. We know, of course, this is going to be natural log of u. Not natural log of me, but natural log of u. Ha, stupid joke, I know. I'm hilarious. Plus c. So that one wasn't so bad. But what if we had something that's just slightly different, enough to throw everything off completely? Let's say we left the numerator alone. Let's say we leave the numerator alone, but instead of that denominator, we had something like this. So you might be tempted to try some pre-calc tricks. You might be tempted to try polynomial long division. You might be tempted to try some of that synthetic division. But there is even a better way than that, considering we have the same degree on top as we have on the bottom. It opens up some new possibilities about different ways we can possibly deal with this. So what does this make you want to do besides run away in terror with your arms over your head? So I see that the top and the bottom both look factorable. I can tell because the top has a square minus a square. If it were a plus, we can't do anything. We can't do anything with the sum of squares because if we were to simplify a sum of squares, we would get the result in terms of some imaginary number, some complex number. Can't do anything with that. So it works out really nicely that we have a difference of squares. So let's go ahead and before we even jump into the calculus, let's simplify this a little bit using some of our pre-calculus tools. So I'm going to factor out the top and pray and hope for the best that this actually works. So x squared minus 25. So remember that when we're doing a difference of squares factoring, suppose we have a squared minus b squared. We can simplify a difference of squares by writing it like this, and this is the fully factored form. Works really nicely. So let's pretend that the a squared is x squared, which means a is going to be x. And let's pretend, or I guess we're not really pretending, let's assign b squared to be 25. So if b squared is 25, then b is going to be 5. So this is going to be x minus 5 times x plus 5. And sometimes this works in our favor. Sometimes it does not. I'm not going to spoil the surprise on this one. So let's see if the bottom can be factored. And it looks like it can indeed. So we want two numbers that add up to whatever happens to be the middle coefficient. We want to add up to -4. We want to multiply to -5. So the two numbers that do that for us would be -5 and +1. So we're going to do x minus 5 times x plus 1. That is our simple algebra 1 quadratic factoring. I keep erasing the exponent when I don't mean to. So now we can see that things get simplified quite a bit. We can yoink this and then yoink this one out of there too. Meaning we're left with, I'm really lazy. I'm not going to rewrite everything. I'm just going to erase the thing that gets canceled. We get left with this right here. Oh, I didn't mean to change the colors. My OCD is going nuts right now. I ought to see if I can get insurance for that. I feel like I might need it one day. OCD insurance. When you're crazy, but you can't afford to be crazy. All right, so this is really similar to what we had in the last example. We can break it up into two separate integrals. We're going to have x over the common denominator. And then we're going to have 5 over the same common denominator, but I'm going to move the 5 out front. So we're going to do something similar to what we did in the last example. We're going to set u to be everything that occurs on the bottom. And then before we solve for du, what I'm going to do is I'm going to solve for x. So I'm going to subtract both sides of this differential equation. It's not a differential equation, it's just an ordinary equation. Subtract both sides by 1, and we get x is equal to u minus 1. Fantastic. And then now I'm going to take the derivative. So I'm going to derivative of u with respect to x. is going to be just 1, and then I'm going to multiply both sides by dx, so we get du is dx. So this is going to be x on top, so x is the same as u minus 1. And then on the bottom is just u, dx is du. And then right here, we can actually do a u substitution problem in our heads to help us handle this one. So theoretically, if we set any variable, I mean, it doesn't have to be u. I'm already using u. So let's say we set w equal to everything on the bottom. So if w is equal to x plus 1, then that means if we take the derivative, we just get dw. So that means it's going to be plus 5 times integral dw over w. And we don't have to do any modifications because the derivative of x plus 1 is just 1. It works out really nicely. So we don't have to divide by any constants in the differential equation like we're used to doing by this point. So this is going to turn into u over u. That's going to be just 1. I'm going to make it its own integral. It's going to be 1 times du. And then we're going to have minus the other integral. It's going to be minus integral of 1 over u. And then what we have next is the antiderivative of du. Remember, that's just going to be u. And then we have 1 over u. The antiderivative of 1 over u is natural log of u. And then this part is going to be plus 5 times natural log of w. And I know I erased it. I apologize about that. But u and w are actually the same in this problem. So u is going to be x plus 1. U is x plus 1. And then we have minus natural log of u, natural log of x plus 1, plus 5 times natural log of w. W is the same as u, which is x plus 1. And again, you can combine like terms if you want, but I would consider this to be a complete answer. You would get full credit if you turned this into my exam. If you did this on one of the exams I set for you, you'd get full points for this. So we are finished. So let's try some more. We're having so much fun. I don't want this to ever end. And that's not just my panic disorder telling me that. Let's say we have something a little bit different. I want to give you guys something that's similar to what we just did, but different enough to warrant doing a completely different example. All right. So at first glance, we can tell that we definitely want to break it up, kind of like how we did in the last two problems. So we're going to make this 1 over the common denominator. That's going to have its very own integral, 1 dx over the denominator. And then we're going to have another integral with a numerator of x over our exact same denominator. I don't know why everything starts looking slanted after a while. I don't know if it's bothering you, but it's bothering me. Really unprofessional of me. Clearly, I graduated top of my class in art school. My drawings are impeccable. So, with this first one, or actually, let's switch things around a little bit. For no good reason at all. So for the first one, we can clearly see it's a u sub problem. So u is going to be 1 plus x squared. And then we're going to take the derivative of both sides and then multiply both sides of that differential equation by the differential dx. And then I don't like the 2 being on the right. I'm going to divide both sides by 2. So we get du over 2 is equal to x times the differential dx. So 1/2 du is equal to x dx. So let's go ahead and make this 1/2 times the integral. And then x dx is the same as 1/2 times du. We have the 1/2, and now we have the du over u. Nice and easy. But then this next part, it doesn't play nicely. The first part played nicely because we had a degree of, the degree of the top was 1 less than the degree, why can't I talk right now? the degree at the top was 1 less than the degree on the bottom. So things work out super, super nicely in that case. We can do a simple U substitution and get a simple answer. But unfortunately, we can't do anything like that for the second integral. We're going to have to do a different kind of a substitution. So if you're not too familiar with trig substitution, I invite you to go check out my previous videos where I do some in-depth examples covering trigonometric substitution, because that's what this next part involves. So I'm not going to get into the details. Like I said, go check out the videos if you're curious about the details and how this particular problem works, but I'm just going to kind of breeze through the trig part of this. So I'm going to use this substitution. I'm going to set x equal to be tangent of theta. And then I'm going to take the derivative of both sides and then multiply both sides by d theta. So dx is going to be secant squared theta. Derivative of tangent is secant squared. So dx is secant squared theta d theta. And then I'm going to square both sides of the original equation. We're going to get x squared is tangent squared theta. And then I'm going to add 1 to both sides of this new equation. So we're going to get x squared plus 1 equals tangent squared theta plus 1. And you might be wondering why I did that. And it's because I want to make this look as closely like what we have in the actual integral as possible. I saw that we have a 1 plus x squared in the bottom. So that's why I decided to add a plus 1 to both sides. I want to make it look identical to what we have in the denominator of the second integral. So we're going to have plus, and then let's substitute everything back in. So dx, we can tell, is just secant squared theta d theta. Just a different form of a change of variables. No different than U substitution. And then on the bottom, we have 1 plus x squared. It's the same as x squared plus 1, which we know to be equal to, oops, forgot to add the 1 right there. That would have ended up really nastily. That would have been really ugly if I forgot that. So x squared plus 1 is tangent squared theta plus 1. That's not our new denominator. It's the same denominator, just written in a different form after that change of variables. So I invite you to take out your trig identity sheet if you don't already have one. You might have one in your pre-calc notes. It might be pretty dusty. You might be needing it for this class. So you're trying to follow along. Maybe you're auditing my class. Maybe you're trying to understand integrals pretty well before taking Calc 3, or maybe you're taking differential equations. I invite you just to have a printout of the trig identities handy, unless you're awesome enough to where you've already memorized all of them, which I have not. I've memorized very few of them. So I have my own trig identity sheet actually pulled up in front of me right now. And I'm going to use one of those with that green identities that tell us that this entire thing right here in the bottom is equal to secant squared of theta. So I'm going to write it off to the side. This is the one we want to use. This is the particular Pythagorean identity that we're going to be using in this problem. So I'm going to replace everything in the denominator with secant squared theta. And it works out really nicely because now we just have 1. And we couldn't do that before. We couldn't do that with an ordinary U substitution. We have to use a trig substitution strictly for this to work. So anything over, oh, I almost committed a faux pas. We can't have 2 differentials there. So we know anything divided by itself is 1, doesn't matter what it is. So this whole thing is just going to be 1 d theta. So just d theta. I'll rewrite it. How many of you are sick of my voice by now? I'm already kind of sick of my own voice, which says a lot. So let's integrate this first part. So we have 1 over u. The antiderivative of 1 over u is going to be natural log of u. So that's going to be 1/2. Oh, we don't need the integral symbol anymore. It's going to be 1/2 natural log of u, and u happens to be 1 plus x squared. Nice. Love it. And then we have d theta. So if the antiderivative of du is u, then the antiderivative of d theta is going to be theta. But we're not quite done yet. We can't leave it in terms of theta because we did a trig substitution. Whenever we do a trig substitution like this, we have to pay careful attention and make sure that we convert things back into the original variable. So this integral right here, it's not an integral anymore, but this part of the answer is in terms of x. We need this to also be in terms of x. We can't have a solution be in terms of 2 different variables, at least not in this class. Later on you can, but not now, not here and now. So how the heck do we convert theta into terms of x? So we want to use this right here. We know that x is equal to the tangent of theta. So how do we solve for theta? So we need to take the arctangent of both sides. So I understand the convention in most math classes is to write it like this. This is an inverse tangent. But in my experience, that just gets way too confusing with cotangent because it's the same. People can think of this as being the same as 1 over tangent of x, which is not the meaning that I'm trying to convey here. So I tend to just steer away from this notation. It gets kind of confusing sometimes. So I'm going to actually just call it arctangent of theta just to prevent any potential confusion. So I'm going to take the arctangent of both sides of this equation. So then arctangent of x is equal to arctangent of tangent of theta, which is just theta. So arctangent of x is equal to just theta. So I'm going to replace this theta down here with arctangent of x. Inverse tangent of x is another way of saying it. The arctangent is the inverse tangent of the argument. In this case, the argument is x plus c. All right. Well, that was fun. I can't think of anything else I'd rather be doing on a Wednesday night at nearly 2 in the morning than getting freaky with some math, especially since my plans fell through. And I'm not just saying that because I want you to feel less sad about me. So I think there might be just one more I wanted to talk about before we call it a night. Let me see if memory serves correctly. So yeah, there is just one more I want us to work on in this video. So let's say we have this expression right here. Nope, I want to use one that I didn't shamelessly rip off from someone else. I want to make this a little bit different. I don't want to completely rip people off. What goes around comes around. Ain't that the truth? All right. So I want you to pause the video. I want you to think about all the methods we talked about in this video, think about all the methods we covered in my previous video, and think about methods you may have covered in other videos not made by me, maybe things you've covered in your calculus class at school. See if you're able to carry this out to the very end. And if not, then you're a little bit stronger from having tried that. You know, the mind is something you need to work out, just like you work out your other muscles at the gym. You get smarter by getting things wrong and going through frustrating things. So whenever you're getting frustrated at a problem, it means you're growing. Kind of like how when you work out at the gym, your muscles get sore, and that's how you know that you are actually getting some significant gains. You're actually getting some results from your workout. So brain pain and frustration means that you are on the right path. You're learning something new. Your brain is getting bigger and stronger. So you should always seek out really difficult problems instead of just doing what's easy all the time. So I invite you to pause the video and try this on your own. All right. So I'm looking at this and I see that the bottom can be factored. And I also see that the bottom has a degree that's 1 higher than the degree on the top. Both of those pieces of information are really good to have at your disposal. It's always a really good idea to know exactly what you have because information like that influences what kind of a strategy you want to use. So I see that the bottom can be factored. It's always a really good idea to factor out the bottom when possible and then see if that helps you at all. Because you might be tempted to do what we did in the last ones. You might be tempted to do something kind of like this, break it up into 2 separate integrals, but that's actually not the best approach to do on this problem. So let's go ahead and factor the bottom. So this is going to factor into an x minus 3 and an x plus 2. And you might be thinking it doesn't really help a whole lot. And initially, it seems like you're right. But we're going to be doing something that's kind of new. This is a strategy I understand that isn't really taught in pre-calc classes anymore. A while ago, it was taught in pre-calculus all the time, and maybe even algebra 2. It's the concept of, I'm going to type it up on the board. It's not the name of it, but I'm going to type the name, PFD. That is partial fractions decomposition. So as you can tell, it has something to do with fractions. That's what my own awesome detective work has led me to infer about it. It has something to do with fractions. But then what about decomposition? What does decomposition mean in the math context? Well, strictly math speaking, it means we're breaking something up into multiple parts. We're applying that concept of modularity that I keep talking about, breaking up a huge problem into small, manageable pieces that we know exactly what to do with. Sure, we don't know what to do with this one, but if we break it up into small pieces, we can eventually get our answer by integrating smaller, more manageable pieces we do know how to integrate. So that's what it means to decompose something from a mathematical perspective. We're just going to be breaking something up into small pieces. So, and let's forget about calculus for now. Let's leave the realm of integration. Let's talk only about this being the function it is and decomposing it before we have even a glimmer of a chance of hope of being able to integrate this, being able to apply some calculus to this situation. So we have two linear factors. We know they're linear factors because we have a degree of 1 right here in the first factor. We have a degree of 1 right here in the second factor. They both have a degree of 1, which means they are both linear factors. And is my name going to be annoying like that, always covering things up? I don't know. I hope not. So we have two linear factors. And whenever we're dealing with a partial fractions decomposition problem like this, whenever we have linear factors on the bottom and then just a single power on top, we need to approach it like this. It's going to be some constant over the first power plus some other constant divided by the second linear binomial divided by x plus 2. So now what we need to do is we need to find these variables. They're variables now, but later on they're going to be just constants. It is possible to solve for a and b, and that is our next step. We need to solve for a and b in order to actually integrate this thing. So how the heck do we do it? How do we find a and b without Wolfram alpha, without cheating? Well, I want to get rid of all fractions. I don't like having fractions in my algebra, so it's always in your best interest to get rid of them if possible. So we have a over x minus 3. I want to find a common denominator. So if this right here is our common denominator, that means this first term is missing x plus 2 in our denominator. So I want to multiply the top and the bottom both by x plus 2. And then this one is missing x minus 3 in its denominator. So I'm going to multiply the top and the bottom of this both by x minus 3. So the nice thing about that is we can multiply everything by the common denominator and all the fractions go away. We no longer have any fractions whatsoever, which is really, really nice. Waiter, there are fractions in my algebra. Can't have that. So how do we solve for a first? Well, to solve for a, I'm interested in making this entire thing become 0. So we want to ask ourselves, what variable would make this entire thing in the shaded box be 0? Well, if x is 3, 3 minus 3 is 0. So this entire thing in the box would just become 0. So I'm going to set x equal to 3. It won't stay 3. I'm just going to set it to 3 for now. You can think of it as just kind of being a placeholder. So x is 3. Let's go ahead and plug 3 in for x and see everything that happens. And again, I'm not just arbitrarily setting a variable equal to 3. I'm just using it to crack this code. And then x is going to be something different in just a moment. Three minus 3. So on the left side, we're going to have 6 minus 3, that's 3, equals, this is going to turn into 5a plus 0. So if we divide both sides by 5, we're going to get a equals 3/5. Sorry about that. I thought I heard someone in my living room. I just rented a new apartment, really, really small, so it just makes it even more freaky whenever I hear kind of like a noise, a random noise out in the living room. Makes who's in my house? Well, joke's on them. They're not going to find anything. I have like the most bachelor fridge you can imagine. I have nothing but condiments and water jugs in there. So joke's on you, burglar. What are you going to find? And if you find, I'll help you find some money. If you're probably not going to find any, but I'll help you find some. So we found A already. We used x equals 3 to help us find A. So we don't need to do anything else with that one. We're going to pick a different value of x now. So now we're interested in finding B. So in order to find B, we need to make everything in this box equal to 0. So x has to be -2 in order to accomplish that. So I'm going to set x equal to -2. Do what I did in the last one. Plug -2 in for x everywhere I see x. X plus 2, that's going to be -2 plus 2 plus 0. Oh, did I mess things up? Oh, no, I didn't. I just did an unnecessary step. B times -2 minus 3. So this is going to be turning into a -4 minus 3. We're going to get a -7. And then the A term is going to go away. It's going to become 0. And then B is going to become, we're going to have a -5B. So then if we divide both sides by a -5, we're going to get B is equal to 7/5. All right, so now that we have those values, now that we have those values, we want to go back to what we started with and actually start applying some calculus. So this is going to be equal to A times everything we have in the first part of our denominator. It's going to be A over x minus 3 plus another integral, B over x plus 2. So let's go ahead and put our values in. So x is equal to 3/5. We can actually move the constants outside just like we're used to. In fact, let's just do that right now. So then this is going to turn into 3/5 times integral of dx over x minus 3. That is the most hideous x I've ever drawn. Plus b, we know b is 7/5. What's going on with my mouse? I don't know why it's doing this dragging thing all of a sudden. B is 7/5. B times the integral is going to be 7/5 times the integral dx over x plus 2. So this is a simple u substitution problem. We can actually do this one in our heads. So if u is x minus 3, that means du is just going to be dx. We don't have to do any manipulation whatsoever, which means we're going to get du over u. That's going to be natural log of u. So we're going to have 3/5 times natural log of our denominator, natural log of x minus 3. I think the burglar in my house must be getting disappointed with my lack of valuable stuff and my lack of will to live. Not even a good aura to feed off of. So that's a relief. And then we're going to do the same thing. If we set u equal to be x minus 2, no, sorry, x plus 2, then du is just going to be dx. That means we're going to have du over u, which is natural log of u, which in this case is natural log of x plus 2 plus c. Bam, we're done. So let's remind ourselves what we did here, what we accomplished. So we started with this thing right here. And ultimately, we ended up with this. So partial fractions decomposition, it seems easy at first, but it gets much, much, much more complicated. So complicated, in fact, that I'm going to be devoting an entirely separate video just to partial fractions decomposition. There are many, many different cases to consider, but I think I've already taken up way too much time making this video. So check out, keep your eye on my YouTube channel. I'm going to be posting a video dedicated only to partial fractions decomposition. Oh, and I realized Sorry. I meant to write PFD and not PDF. This isn't a PDF. This is PFD, partial fractions decomposition. So I'm going to be making a completely separate video just for this topic. So keep an eye on the YouTube channel. It should be coming out. I hate making promises because I know I'm just destined to break promises. So all I'm going to say is it'll be there soon. All right. Hope this has been informative, maybe even entertaining. Have a wonderful night, you guys. Have a wonderful week, and I'll see you in the next video.